3.3 is just about the reverse of 3.2. So in 3.2 we said that if we have a transversal cutting through two parallel lines, that we get all of these nice angle relationships. Well, 3.2 or 3.3 is about how all of that goes the opposite direction too. So basically what we were talking about in 3.2 is that say you have two parallel lines and they're cut by a transversal, then we could say that corresponding angles are going to be congruent to each other. We can say that if we look at, say, angle 1 here and this angle here, those are going to be alternate interior angles, so they're congruent. We get all these nice congruences. Well, in 3.3, we're going to be going the other way. So we're going to not start with the fact that the lines are parallel and then go to the angles being congruent. We're going to start with the angles being congruent and show that that tells us that the lines are parallel. So it goes both ways. So if the lines are parallel, then the angles are congruent. Or if the angles are congruent, that means the lines must be parallel as well. So that's what we're going to be talking about in 3.3, going the opposite direction as we did in 3.2. So postulate 16 here is the converse to the corresponding angles postulate. So if you remember converse, that means we take, if we have an if-then statement, the converse is we switch the if part with the then part. We just switch those around. So the converse is exactly that. So instead of saying if you have two parallel lines, then the angles are congruent, say corresponding angles are congruent, we're switching that around. We're taking the converse. We're saying if you have corresponding angles congruent, that means then that you have parallel lines. So that is postulate 16. All right, let's look at example 1. So we're going to apply this converse. So what the instructions say here is to find the value of x that makes m parallel to n. So, we could plug in all kinds of stuff for x and make those angles whatever we want them to be. But if we want these lines to be parallel, then that means that 71 and 2x plus 3 must be equal to each other. So we can take 71, set it equal to 2x plus 3, and find the value of x that will make that true. So that's what we're doing when we're solving an equation. We're finding the value of x that makes this equation true. That's what we're doing when we solve. So let's go ahead and do that. We can start by subtracting 3 from both sides, and we get 2x equals 68. Then we can divide both sides by 2, and we get x equals 34. So that means if we were to take 34 for x and plug it in here, we would get 71 here, which would make 71 and 71 for those two angles, which would mean that we have corresponding angles that are congruent, and that would mean that the lines must be parallel. All right, 3.4, alternate interior angles, converse. So again, the regular theorem about alternate interior angles is that if you have two parallel lines, then alternate interior angles are congruent. This is the converse, so we flip that around. We say if we have alternate interior angles that are congruent, then the lines must be parallel. Same thing with alternate exterior angles, exact same argument. And then same thing with 3.6, consecutive interior angles converse, except again, this is the one where they're not congruent. This is where they are supplementary. So if we find that, say, angles 3 and 5 here do in fact add up to 180 degrees, that will tell us that lines L and K, or J and K, excuse me, must be parallel to each other. In example 2, we're given some pictures and asked if we have enough information to determine that these two lines are parallel to each other. So that's lines A and B. So in example A here, we have this angle and this angle marked congruent to each other. So first of all, these are exterior angles. So the two lines in question are these two, and they're being cut by this horizontal transversal. And so we've got the two angles on the exterior of the two lines, and they're also on different sides of the transversal. So one is on top of the transversal and one is on bottom of the transversal. This makes them alternate exterior angles. So by 3.5, theorem 3.5, the alternate exterior angles converse, that tells us that since these two angles are congruent, they must be parallel. So yes, lines A and B are parallel here. For part B, we have corresponding angles. So these are both in the bottom right spot of each intersection. So that makes them corresponding angles. And they're marked congruent. So we can say then by the alternate, I'm sorry, that's this one up here. by the corresponding angles converse. If we have corresponding angles that are congruent, that means that the lines are parallel. So yes, these lines are parallel to each other. And for part C, we were told that the measure of angle 1 plus the measure of angle 2 is 180 degrees. So is that enough to tell that these two lines, whether or not these two lines are parallel to each other? Well, we don't have enough information here. So what the equation here is kind of going for is trying to look at something like consecutive interior angles. So if these two angles, if 1 and 2 were on the same side of the transversal, if they were either both on top or both on bottom, and we knew that they were supplementary, so we knew if we add them up to, if we add them together, we'd get 180, then yeah, we would know that they're parallel. But these are not consecutive interior angles, they are alternate interior angles. And so in order to tell that A and B are parallel, we would need to know that angles 1 and 2 are exactly the same, that they are congruent to each other. So here we could have it where they add up to 180 and that they're parallel. So like if they were both 90 degrees, then that would make the lines parallel. But it could be any number of other things. So there's not enough information here. Okay, flip to the back side. And let's take a look at example 3. So it says find the value of x that makes m parallel to n. So line m is this one here. Line n is this one here. And we want to find the value of x that makes these two lines parallel to each other. Well, the things that we have expressions for right here and right here, these are outside of the two lines, so that makes them exterior angles. And one's on top and one's on bottom of the transversal, so that makes them alternate angles. So these are alternate exterior angles. And we know that if we want the lines to be parallel, then the alternate exterior angles need to be the same. So if we take 180 minus x and set that equal to x, that would tell us that this angle must be the same as this angle. So let's set them equal and find what value of x will make these two things equal to each other. So if we add x to both sides of the equation, that will get rid of it there, and we'll get 180 is equal to 2x. And then we can divide by 2. And so we get that x is equal to 90. So if we set x equal to 90 and then plug that in here, that will give us two 90-degree angles for those, which are going to be the same as each other. So two 90-degree angles are congruent to each other. And that tells us that the lines must be parallel. Example 4. Find the value of x that makes line m parallel to line n. So again, we've got to find the value that makes this set of angles have the property that makes the lines parallel. Now in this case, they're not going to be congruent. So this angle right here that's described by x minus 15, and this angle right here that's described by 80, these are consecutive interior angles. So interior because they're between the two lines, consecutive because they're one right after another. They're on the same side of the transversal. So this makes them consecutive interior angles, which means then if the lines are going to be parallel, these two angles have to be supplementary. So if we take x minus 15 and add to it 80, we should get 180. So let's combine like terms here. Negative 15 and positive 80 makes 65. And then we can subtract 65 from both sides to get that x must be 115. And that's it. So again, in the instructions here, we were not asked to find the angles. We were just asked to find the value of x that makes those lines parallel, and that value of x is going to be 115. Let's look at theorem 3.7. So this is called the transitive property of parallel lines. Well, if you remember the transitive property, that was the thing that says that if A is equal to B and B is equal to C, that tells us that both A and B are equal to the same thing, so they must then be equal to each other. So if that's true, that means that A must be equal to C. So we can apply the transitive property to parallel lines too. So parallel lines will be transferred through the transitive property. So if two lines are parallel to the same line, then they must be parallel to each other. So let's say that if P is parallel to Q, and then Q is parallel to R, well, that tells us that P must be parallel to R as well. Again, this double line here, that means parallel to. So this says that If P is parallel to Q and Q is parallel to R, then P must be parallel to R. And in example 5, this is fairly straightforward, but this is just an example of exactly that theorem. So it says that each utility pole shown here is parallel to the pole immediately to its right. Explain why the leftmost pole is parallel to the rightmost pole. Well, okay, let's again start with the fact that each pole is parallel to the one to the right of it. So that means this pole is parallel to this pole, so we could mark those parallel. And this pole is parallel to that one, and this one's parallel to that one, and these are all parallel to all of the other ones. So that the parallelness kind of transfers through these lines so that they're all parallel to each other.